With this video, we're going to do a slight switch away from the entity relationship models and schema and stuff like that to talking about database theory really as theory. We'll be doing a bit of proofs, a bit of algorithms in which to determine how do you structure a table that can contain many attributes, it contains all the information you want, into smaller tables that has just the information you want in each table in ways that will reduce redundancy and data duplication and things like that. All right, the way that we handle this is by talking about what are called normal forms. These are basically ways that your database is structured such that it guarantees a particular set of properties. We'll talk about these really as we come across them, and you'll understand why each particular type of normal form is useful for different reasons. Okay, so the first thing we're going to do is we're going to talk about the first and simplest normal form. That is called the first normal form. And we'll have to talk about a little bit about some vocabulary. One thing is the word atomic with respect to databases. A domain or an attribute is atomic if its elements are considered to be indivisible units, meaning that there's not more structure underneath them. Okay? Why do we call atoms atomic? It's because you can't break atoms apart. At least that's what people used to think until we, invented nuclear bombs. Okay. So some examples of non-atomic domains are things like sets of names, like lists, and composite attributes, things that have multiple parts. They're composite, which is the opposite of atomic. Sometimes these things are harder to just catch at. For instance, identification numbers like CS480, these can be broken up into parts, and so they're really not atomic. There's actually two parts here. There's the department part, and then there's the department course number part. Those are actually two things being squashed together, making this value not atomic anymore. And what we say is a relational schema, or really just like a database, we say a relational schema R is in the first normal form if the domains of all of the attributes of R are atomic, meaning all of the attributes only hold atomic data. All right, for example, the reason why we're even talking about this is non-atomic values, things like CS480 or things like a list of friends separated by spaces or something like that. Non-atomic values complicate storage and encourage redundancy. So for instance, let's say we have a set of accounts that's stored with each customer, and we have a set of customers stored with each account. Each account can involve multiple customers, and each customer can have multiple accounts. If we have this set of accounts associated with each customer, it becomes really hard to say, is this customer part of this account? Because we'd have to look through this atomic data type. We'd have to reach into a particular element and say, oh, is this customer ID number anywhere in this list? In reality, it's better to structure your data to be atomic so that the database itself can say, oh, I can really easily combine rows. I can really easily join things to determine the correct answer here. And for the purposes of this class, we're going to assume all relations here are in the first normal form. It really doesn't ever make sense to not have your database in first normal form. Even though it's sometimes really easy to have things like CS480 as a ID, it's better to break that up into two parts. You have the department CS and you have the course number 101. And then you can do more easily structure your data so that you can do things like find all of these CS classes. Well, you don't have to look into each element and find which classes have CS in the beginning of their name. You just look at which column is the department for all of those attributes. Oh. So the important thing to note here is what is atomic depends a bit on your use case. For example, strings are normally considered indivisible. Usually, most of the time you're storing text in your database, it doesn't really make sense to care about the particular characters in the string. However, there are times when strings aren't indivisible. For example, when we had the course number example. Even though we have a string, CS here, 0012, this is a string, it really is divisible here because it does have structure within it. And so because we can grab the first two characters to find the department, the domain course numbers is no longer atomic. CS here, CS0021 actually has multiple parts and really should be broken up into different attributes. And once again, the reason why atomicity is good is because it leads to, the reason why it's bad to have composite values is because it means the application program has to be able to interpret these composite values. So the application program has to be smart enough to know the first 2 characters is the department. And the database can't ensure that, for instance, the first 2 characters are a meaningful department, or that the first 2 characters can make sense, or that somebody didn't accidentally write CSE480 and screws up all the application programs later. All right, so that's first normal form, making sure all of your things are atomic. And what we're going to do is we're going to talk about, in general, kind of what we care about is trying to convert databases into these better forms. Now, how do you convert a database to be first normal form? Well, that's really just depending on making sure you have attributes that don't have composite parts. There's no real algorithm to do that other than really just using your brain. However, the next normal forms we're going to be talking about require a little bit more stuff to handle. Okay, so the goal in general is to decide whether a particular relation, a particular table, is in a good form. And now what is good? Well, that will depend a lot on which normal form and what attributes of normal forms you care about. Okay? So the way that this generally works is if we find that the relation R is not in a good form, we decompose it. We break it up into smaller subrelations, relation 1, 2 to relation n, such that each subrelation is in a good form. It does match the properties we want. The other rule that must be the case is that the decomposition must be a lossless join decomposition. What does this mean? It means that if you join these subrelations back together, you get back the original big relation. It means that there's no loss of information by breaking up your relationship into these subrelations. All of the data is still there. And the theory that we're going to use to determine whether a relation is in a good form is based on functional dependencies and multi-value dependencies, both of which we'll be talking about in a little bit. All right, so these dependencies will let us capture the fact that there are certain constraints, certain expectations that data being added to this relationship will follow. Okay, so how do we know if we can decompose a relation into subrelations? Well, we need to look at constraints. We need to look at how the data will be formed. Because if we don't have any relationship between attributes, we have no way of knowing, our names associated with particular grades, associated with particular groups. We'd have no way to break apart this because we have no way of identifying things like keys. We'd have no way of identifying important attributes that we can use to join on. So in the previous example, every team had a grade, and that grade was shared by every member of that team. Okay? And so if you told me the team's name, I could tell you the grade, because every team has one and only one grade. And this is called a functional dependency, often abbreviated by FD, because we'll be saying that a lot. And if I say the team's name functionally determines the grade, meaning if I give you the team, you can give me the grade, the way that this is represented is with an arrow from team pointing at the grade. And we can use these dependencies to identify redundancies in our relation. We could say, okay, if I know that a team always determines the grade, I don't need to have multiple copies of saying this team belongs to this, has this grade, and this same team also has this same grade. That's redundant information now. And so a more formal way to say that, X functionally determines Y is an assertion about the relationship R that whenever there are two tuples on R agree on all of the attributes of X, if multiple rows have the same team, then they must also agree on the attributes in the set Y, meaning if rows have the same team, they must have the same grade. And so we often say X functionally determined Y holds in R, and just by convention, X, Y, and Z represent sets of attributes, and A, B, and C represent single attributes. I won't really be hammering this home, but this is just in case you're trying to follow some of the notation that I'm doing here. And the other thing is, in general, I don't write set formers for sets of attributes in order to simplify some of these models. So I'll just say, A, B, C instead of using the set notation with the curly brackets and commas there just to make my life a little bit easier. Okay, so multiple choice question time. For this particular relation, comments, does it obey the functional dependency, MSU ID and year functionally determines name and age? All right, so let's go through this. So first row, our MSU ID is Nahum Joss, and our year is 2016. Are there any rows that both have Nahum Joss and 2016 other than this first row? No, they're not. So the fact that Nahum Joss in 2016 functionally determines Josh 27, that's already the case. Yeah, there's nobody conflicts. Nobody has the same Nahum Joss in 2016 and has different information for name and age. Okay, next one. We have Stacy 123 and 2015. Are there any rows that match these attributes? No. So if I give you Stacy 123 and I give you 2015, you can say, oh, I know the name. The name is Stacy and the age is 22. Okay. The next one, Jenny 456, 2014. Are there any rows that match Jenny 456 and 2014? Yeah, the one right below it. Okay. Now, okay, so that's not a problem in and of itself. We have two rows with the same left side of the functional dependency. Do they agree on the age and the name? Yeah, both of them both say age is 22. Both of them both say the first name is Jenny. So we're okay. We also have another MSU ID year combination, Jenny 456 and the year 2015. Does this match with any other rows? No, so that's fine. And then the last row we have other Josh and 2016. Does this match with any other rows? No, so we're fine. So does this relation obey the functional dependency MSU ID and year determines name and age? The answer here is yes. All right, now it doesn't, MSU ID and year doesn't determine, for instance, comments, because we have two rows that match MSU ID and year but have different values for comments. So that functional dependency is not true, but I didn't ask you about that one. So the correct answer here is, does comments obey MSU ID year functionally determines name and age? It does. All right, so let's go back and let's talk about ways in which you can determine functional dependencies. Now, the best way often to determine these are things from common sense, where if I give you a piece of information, you can infer the rest of it. Though some of them are slightly more complicated to come up with. One type of kind of common sense FD is things like no two courses can meet in the same room at the same time. Let's pretend that was a rule that holds at MSU. Okay? So that means if I give you the hour and I give you the room, you can determine the course that is there. And there could never be another course that also has that same hour and that same room but has a different course. So we have the functional dependency here. Give you the hour, give you the room. I can determine the course that's being taught in there at that time. There are some other more common sense ones. For instance here, let's imagine we have a relation that has a start time, end time, and a duration. Which of these are logical functional dependencies? All right, so let's go through the first one. If I give you the start time, can you tell me the end time and the duration? No, there might be multiple events that start at the same time but have different end times and consequently different durations. So the first one is not a good functional dependency. But if I give you the start time and the duration, you should always be able to tell me a unique, or not a unique, but you should always be able to tell me what is the end time. You can do the math to determine what the end time is. If I give you the end time and the duration, you could also do the math and figure out what the start time should be. And if I give you the start time and the end time, you can also tell me the duration. So the answers 2, 3, and 4 are all functional dependencies that are really logical functional dependencies. They must be the case. However, the first one is not. However, the first one could be a functional dependency if you had additional information. Like, for instance, if you knew that every start time was unique, like we're doing the start times for a given day in a particular room, we know there's no two rows that have the same start time, in which case start time would functionally determine every other attribute in this relation. But I didn't tell you that, so you couldn't necessarily know that for sure. However, 2, 3, and 4, assuming that start time plus duration equals end time, you can always infer those lower 3. All right. Some more rules regarding how to handle functional dependencies. So if I have a functional dependency like X functionally determines A1, A2, AN, so forth, this means the same thing as X functionally determines A1, and then there's another functional dependency which is X functionally determines A2, and there's another that's so forth and so forth, saying X functionally determines each thing on the right side of the functional dependency. A way to do that with better words, so in our previous example, MSU ID and year mapped to name and age, or functionally determines name and age, is the same thing as breaking these up into two functional dependencies, MSUID and year functionally determines name, MSUID and year functionally determines name. Okay? Now, there is no rule for splitting the left sides. Why is that? Well, it really doesn't make any sense. So if I need the MSUID and the year to determine the name, if I just gave you the MSUID, could you give me the name? No, you need both of those components to do the functional dependency. So there's no easy way to split up the left side of functional dependencies. All right, a little bit more vocabulary here. There are such things as trivial functional dependencies. All right, what is a trivial functional dependency? A trivial functional dependency is if I don't even need to know anything about X and Y to tell you that it's true. Okay, so for example, if I give you the customer name and I give you a loan number and say this functionally determines customer name, well, you would say, well, that's pretty obvious. If you give me the name, I know what the name is. You can give me the name and the loan number. I don't care. If you give me the name and the loan number, I can tell you what the name is. Or even simpler, if I give you the name, that functionally determines the name. These are trivial in the sense that they don't actually add any information about the database. Of course, if you have a name, you know what the name is. In general, you would say that X functionally determines Y is trivial if all of the attributes in Y are a subset of the attributes of X. If the things on the right side are already on the left side. Okay, so multiple choice question time. Which of these are trivial functional dependencies? Alright, so let's go through them. If I give you the gender and the age and it functionally determines the height, is this a trivial functional dependency? No, it's not. If I give you the type and the move, and this functionally determines move and damage, is this trivial? The answer here is it's actually not. Now, of course, it's kind of like partly trivial. Obviously, if I give you the move, I can determine the move on the right side. But however, the fact that all the things on the right side aren't part of the left, you could call this kind of partially trivial. But the answer here is number 2 trivial? It's not, because you still are gaining information. Given the type and the move, you can determine damage. This is information you didn't have before I handed you this functional dependency. If I have an ID and a first name and a last name, and this functionally determines the ID and the first name, is this trivial? Yes, because both ID and first name are on the things on the right side are also on the left side. There's no information to be gained here.